Hello and good morning, everyone, and thank you for joining us for our Ansys Virtual Academy, where today's session will be covering the introduction to multi-phase flow modeling in Ansys Fluent. My name is John Dow. I am your host today, and I'd like to introduce to you my colleague, Snegda is our applications engineer who specializes in CFD, and she'll be walking you through the introduction to multi-phase flow in Ansys Fluent. Snigdha,
Thank,
you want to take it away?
sure. Thank you, John. Can you hear me?
Loud and clear.
Awesome. Hi, everyone. Thank you so much for joining us today. Welcome back in 2021. We're going to be continuing our AVA series. I'm Snigdha Sarkar, CFD Application Engineer here at KETIV. Like John mentioned, today we're going to be talking about multi-phase flow modeling using Ansys Fluent. And I'm really excited for this session because of the vast majority of industrial applications that cover multi-phase flows or involve multi-phase flows that could use CFD. So for today's agenda, I'm going to be covering three main things. Firstly, I'll talk about some of the more common industrial applications wherein we can use Ansys CFD for modeling the multi-phase flows. And this is just an introduction for anybody who has not, delved into multi-phase flow modeling yet, but would like to try it out. Secondly, I'll talk about the different classifications of multi-phase flows. Because there are so many different applications, it is very important to be able to classify your unique application in the right category. And that'll help you set up the most accurate, most efficient modeling approach, no matter which CFD solver you use. And lastly, I'll be talking about a simple demonstration case in Ansys Fluent, wherein I'll be showing how can you set up a simple multi-phase flow problem using the GUI. So with that, let's begin today's session. Now, even before I delve into the applications of multi-phase flows, for those of you who are unfamiliar with the term, I just want to go into the basics of what multi-phase flows actually comprise of. As the name suggests, any flow domain that consists a mixture of two or more distinct separate phases would qualify as a multi-phase flow. When I say distinct phases, what I basically mean is that they're not mixed at the molecular level. Once they're mixed at the molecular level, they become multi-species. So for them to be classified as multi-phase flows, you need to have distinct separate phases, right? They could be gases, solids, or liquids, the individual phases. They could be, a mixture of all three. Depending on which application you're solving, you'll be able to classify your multi-phase flow regime based on the individual phases that you see. And lastly, they can be both natural or industrial applications. If you're simply boiling water in your saucepan, then, it's almost like a natural application wherein you can see the evaporation part and changing of phase from the liquid to the gaseous phase. Or if you're talking about more commonly seen industrial applications, you'll see so many of them, from cavitation to evaporation, condensation, to phase separators. There are too many to kind of cover in a single session. Speaking of applications, like I said, there is a vast majority of applications out there. Each of these multi-phase flow application requires a different modeling approach, purely because with multi-phase flows, one of the biggest challenges is that you're not able to predict the dynamic behavior of phase transport in your domain purely on the basis of testing. And that is where CFD can really help you, because CFD gives you that advantage of being able to, study these unsteady dynamic, phenomena in a very detailed way. So you can do the analysis, look at the issues that your product might be facing, and then improve your product based on the knowledge that you gain from these CFD applications. It could also be a process improvement initiative. On the slide over here, you see some of the more commonly seen applications. Of course, cavitation is a widely known application when it comes to multi-phase flows. You can see it mostly in the turbo machinery industry, or if you're looking at the defense industry, if you're looking at spray modeling, jet modeling, you will see multi-phase flows commonly prevalent in those situations. You also have free surface flows, whether it be the transmission for a gearbox, or if you're looking at mixing tanks or river banks, free surface flows are also quite common. And then you have your cooling applications, wherein you'll usually see refrigeration or phase change, evaporation, condensation, for example, in the case of this electric motor, which is being cooled by the oil spray. So really, a vast majority of applications wherein you can use CFD to be able to predict performances better and perhaps come up with products that have better efficiencies, better life cycles. One of the applications that I really wanted to highlight, especially in the context of recent times, is we're all going through a pandemic, and Ansys has made some phenomenal progress in being able to predict what kind of trajectory cough particles might take in an enclosed airspace. This is again one very important multi-phase flow application wherein we can discretely track the particles of cough that are being exhaled by a coughing passenger, say in an air cabin, and see how they travel over a course of time, and if there's any recirculation or if there are any areas of concern. So really, being able to use CFD in your day-to-day life to be able to solve those relevant applications is definitely a benefit. And, in order to do something of this sort, just having that basic knowledge of setting up your multi-phase simulations would be really helpful. Now, because we talked about so many different multi-phase applications, it is important we classify them into different flow regimes. The classification is really like a first step for you to understand how to go about modeling your unique application. Of course, because you have so many different varieties of multi-phase flows, I'll not be able to cover all of them uniquely, but this session is just designed to be an introduction to the basics. There's a lot of information available online, but if you needed help with your own particular application, please feel free to reach out to us. Our contact information will be in the chat box, and towards the end of the presentation, we'll definitely like to have a chat with you and understand how Ansys can fit in your particular application requirement, especially if it's a multi-phase one. So having talked about the classification, let's talk about the basics of how to go about categorizing these multi-phase flows. Like I said earlier, you could look at the classification on the basis of what phases you have in your flow regime. You could have a gas liquid or a liquid liquid flow. You could have a gas solid flow. You could have a liquid solid flow, and you could have a flow in which all three phases exist in some form or another, right? In the case of a gas liquid or a liquid liquid flow, you'll either have a bubbly flow wherein you have gas particles dispersed in a continuous liquid phase, or you could have a droplet flow wherein you'll see the vice versa, wherein you have liquid particles dispersed in a continuous gas flow. You could also have slug flow, in which you have large gaseous bubbles being transported in a continuous liquid phase. And then lastly, you could have a free surface to stratified flow. In the case of immiscible fluids, wherein you have a liquid-liquid flow regime, you could have a clear boundary, a clear interface between those two different distinct phases. On the right here, you can see, a hydrodynamic wave loading on ship, which would be a classic example of a free surface flow. For gas solid flows, you usually have either gas suspended in, either solid particles suspended in gas, just like in the case of particle laden flow, or you could also have pneumatic transport, wherein, you'll have a flow like dune flow, wherein your solid particles are being transported because of the Reynolds number of the surrounding continuous phase. You could also have something called a fluidized bed, wherein you have solid particles, at the bottom of your, fluidized bed, and then you basically inject an airstream into it that results in the suspension of these solid particles in the continuous gas phase. They could further be classified based on how dense or dilute the solid particle loading is. So if this is an application that is more relevant to you, feel free to reach out to us. We'll be able to jump into the more specific details of being able to model this sort of an application. And then you also have liquid solid flows, wherein you have heavy particulate or solid loading, and it's being transported in a liquid. For example, in the case of slurry flow, slurries are quite common in the waste management and process industries. As the picture on the right shows, you have solid particles being transported in bulk. And again, with slurry flow, usually your Stokes number is less than 1. It depends a lot on your solid particle properties, how the flow behaves over time. In sedimentation, as the name suggests, you'll have uniformly dispersed solid particles that eventually settle down at the bottom of the container over the period of time. And then you have a clear demarcation between the solid phase and the liquid phase after some time has passed. So these are all the different classifications of the flows that you might be interested in. And depending on which type of flow you're modeling, you might have to choose different approaches in your CFD solver. So what are the two main approaches in Ansys Fluent to solving these multi-phase flows? The first approach is called an Euler-Euler model. In the Euler-Euler model, what happens is that the phases are treated as interpenetrating continua. That means that the dispersed phase or the dispersed particles, they are not being tracked individually. So we basically solve a single set of equation to understand, where you have concentration of the continuous phase and where you have concentration of the dispersed phase. But the particles are not individually tracked. In the Euler-Lagrangian model, however, which is also called Lagrangian model for the sake of simplicity, individual particles, bubbles, droplets are being tracked. So they are being tracked individually instead of being considered as a separate continuous phase. So on the right here, I think the image is a little bit more helpful in understanding the two different approaches. In a separated system, you would consider those two phases as continuous mediums. But in the dispersed system, you'll have a continuous phase, and then the dispersed particles are being tracked individually. So for today's AVA session, we're going to concentrate on the Eulerian model at the top over here, because this is the more simpler, the more basic approach. And, it is applicable to a lot of different industrial applications. But if you like this AVA, please, leave a comment, or, please give us your feedback, and we can have future AVA sessions that delve deeper into the Lagrangian models and discrete phase methods. So once you've decided that, your application is suitable for the Eulerian approach, wherein perhaps you could treat the two phases as continuous mediums, then, you have to decide which modeling approach or which model do you choose within Ansys Fluent. So there are 3 different models that you can choose using the Eulerian approach. And the commonality between all these 3 models is that, both these phases, or, how many phases you have in your computational domain, they will be treated as interpenetrating continua. So in the VOF model, which is the volume of fluid model, what we are interested in is being able to track the boundary between two or more different phases. This boundary, this interface is of interest to us. So for example, if you were doing a free surface flow wherein you have a riverbank and you're modeling, the waves, for example, the shape of the waves, then, you would choose a VOF model. If you were looking at, a mixing tank problem or, a tank filling problem, and you want to understand how the interface behaves over a period of time, then you would choose the volume of fluid model. In this case, only one set of equation is solved for, all the different phases that you have in your computational domain. So a single set of conservation equations are solved. In the second model, under the Eulerian approach, you have the mixture model. In the mixture model, you have the phases that are treated as interpenetrating continua, and there may not be a well-defined boundary or an interface between these phases that exist in your domain. So for example, if you're doing a cavitation problem, you're just interested in understanding which regions are cavitated. You're not really interested in understanding the bubble boundary or the interface between the cavitating bubbles and the continuous fluid. You're just interested in understanding which concentration is more in which region of your domain. So in those sort of situations, you would use the mixture model. And lastly, you have the Eulerian model, which is the most detailed, most advanced model. Why? Because it solves the conservation equations not as a whole for the entire mixture, but for each of the individual phases that exist in your computational domain. Eulerian model is usually used more in cases wherein you want very accurate solutions, wherein your physics is very complicated and it can't be accurately captured by approximations. So in those sort of situations, you would go ahead and use the Eulerian model. But for today's demonstration, I'm going to be sticking to the volume of fluid model so that we can clearly see the interface between two different phases and how easy it is to capture using Ansys Fluent. Now, at any point, if you guys have any questions, feel free to leave that in the Q&A box, and I will be, taking those questions towards the end of the presentation. So if anything is unclear, let us know. So going back to the VOF model, because I'm going to be doing the demonstration based on this model, I thought it will be beneficial to explain some basics that are true not only for the VOF model, but also for the mixture model. Now, what is the basic concept of treating your phases in using the Eulerian approach? The idea is that you have a volume, which is your total volume, and that is being divided by the different phases that exist in your domain. So for example, right now we have two different phases, phase P and phase Q, and there's a certain volume that is being occupied by the dispersed phase P, and there's a certain volume that is being occupied by the continuous phase Q, right? So if V is the total volume, then VP plus VQ constitutes the entire domain, right? Which is what we see in the box over here. Now, based on this approximation, we come up with the concept of a volume fraction. What is the volume fraction of any one particular phase? It is simply the ratio of the volume occupied by that phase divided by the total computational domain. Going by that logic, the volume fraction of the dispersed phase P and the continuous phase Q would add up to 1. And this basically forms the crux of your modeling when it comes to the VOF model and the mixture model, that only one set of conservation equation is solved for the entire mixture, and the fluxes between those phases is being calculated based on the volume fraction in different regions. Now, the previous concept was common to both VOF and the mixture model. But what is unique about the VOF model is it is used in those situations where you want to understand what is the shape and position of the boundary or the interface between the different phases in your domain. So for example, on the right over here, if you look at the computational grid, we are looking at the volume fraction of any particular phase. If the volume fraction of that phase in a domain or in a cell grid turns out to be 0 after the equations are solved, that means there is no volume of that particular phase in that grid. And if the volume fraction is 1, then based on what we saw in the previous slide, that cell is completely occupied by that particular phase. So it automatically means that if in any particular cell grid, the volume fraction is between 0 and 1, then that is the cell grid that contains the boundary or the interface that we are interested in. So you will notice all of these cells that have a volume fraction between 0 and 1 contain the boundary between these two phases. Now, just calculating the volume fraction is not enough to accurately determine or predict the shape of the boundary. Why? Because your computational grid might be too big, right? So we need to accurately predict what is the shape of the boundary in that particular cell. How do we go about doing that? What we can do is we can take the gradient of the volume fraction in all these cells, and that would give us a normal direction to the interface. So any plane that is perpendicular to this normal direction will automatically constitute the shape of the boundary. And this is being reconstructed as and when the solution keeps solving. Mostly VOF simulations are unsteady in nature because we are tracking the shape of the interface over a course of time. And in those situations, as the time steps progress and the conservation equations keep getting solved, this boundary changes dynamically depending on the values of the volume fraction and the different forces that are acting on the phases. So hopefully this gives you a basic understanding of how the VOF model goes about tracking this interface, this boundary that exists between different phases. So with that, we'll step into the demo, wherein I will be using the VOF model to solve such a problem. Now, the demo is a simple tank filling and emptying problem. What we basically have is a tank that has some initial level of water in it, and then we start pouring more water inside the tank for a given period of time. Because the level of water in the tank increases after we have some more water coming in from the inlet, you see a siphoning effect towards the end, wherein the tank starts emptying because of the gravitational pull. So we're going to be simulating this dynamic behavior and tracking the interface between the air and the water phases inside the tank. So with that, I'm going to go ahead and step into Fluent.
Hey, Snigdha, I believe are you working in Fluent right now?
Not yet.
We just see your PowerPoint.
Yeah.
Oh, okay, sorry.
Give me 1 second. Can you see my Fluent now, John?
Yes.
Okay,
Thank you.
awesome. All right. So if you guys can see my screen, we have a basic 2D model over here, just, for the sake of saving time. What we have is this tank over here that's initially going to be filled with water up to a certain level. And then we have an inlet over here wherein we will be specifying mass flow rate for water to come in. As the tank keeps filling over time, some of the water, will start siphoning out, and eventually it'll result in the emptying of the tank. So I'm going to set this up. And this is really relevant to anybody who's doing, mixing tank problems, because they would also have to, apply some of the initialization and boundary condition and multi-phase model setup options that I show in the demonstration today. So I'm going to go ahead and just for the sake of clarity, read in a new case real quick. And just in case anybody is wondering, I'm using the Ansys Fluent 2021 R1. It is the latest release. We will be having an AVA pretty soon, discussing some of the newer features and capabilities that you'll have access to with 2021 R1. So that is definitely in the pipeline. But let's get back to this demonstration over here. So this is already a case that has been set up. So I'm going to go over all the options and selections that we have chosen. So in the units, we have chosen centimeter as the length. And in this case, because we have that initial condition that the tank is already filled with water up to a certain level, we will have to mark off a certain area that is filled with water. So in such cases, when you're trying to patch in initial values, it's important to make sure that the mesh has the correct unit specified. And like I said, this is a transient problem. We're going to be stopping the influx of water after a certain amount of time. So I have chosen the transient option in the solver. Also, we've turned on gravity and specified minus 9.81 as the acceleration due to gravity. Now coming back to the setup, let's focus on the multi-phase volume of fluid approach. So anytime you have to turn on the multi-phase simulation option, you come to this model setup over here, and you choose whichever model you want to apply to your application. In this case, like I said, we will be tracking the interface, so we'll go ahead and choose volume of fluid. And there are some default conditions that are always checked when you choose VOF model. For example, usually explicit formulation is checked, but I'll tell you why it has been chosen for this particular application. This is a transient problem. Usually when you're doing a transient problem, using an explicit formulation is better because it gives you more, clear, more crisp boundaries or interfaces. And it's also a little bit more accurate. Implicit option can be used with both steady and unsteady problems. Explicit is only available for unsteady cases, right? We're also going to be choosing the sharp interface modeling in the type. And this is because we want to see a sharp boundary between the two different phases. If I were to choose something like dispersed, then the boundary would be a little bit more diffused, but it can give you a little bit more robustness when it comes to the solving. We're also going to go ahead and select the implicit body force option over here. This option is usually chosen when you have high body forces in your particular application. So if you think there's going to be a lot of effect due to body forces, for example, in turbo machinery, or if you're looking at surface tension forces, then make sure that this option is checked. At the top over here, you will notice that the number of Eulerian phases has been automatically set to 2. And that's the default because they expect you to have at least 2 phases in your problem to call it a multi-phase problem. In our particular problem, it'll be water and air. So once you've selected all the relevant options in this tab, you could go and change the tab to phases. And in this tab, what you basically do is specify which phase is your primary phase and which phase is your secondary phase. In the case of VOF, it doesn't matter that much which you make primary and which you make secondary. But keep in mind that if you're using initial patches, or if you're initializing the volume fraction of any one particular phase in your model, then it'll only let you do that for the secondary phase and not for the primary phase. So since I want to patch in the volume fraction of air towards the end, I have chosen air as my secondary phase and water as my primary phase. So you can simply select the material from the drop-down menu. Right now, water has been chosen as my primary phase. And if you go to the secondary phase, you can see that it's air. Now, after you've specified all this, you can go to the phase interaction tab. and choose how your phases are interacting. Now, keep in mind that in this case, I am not doing any heat transfer analysis, and there is no interaction, thermal interaction between my two different phases. But if you were to do a phase change problem, wherein you would see evaporation, condensation, or even mass transfer for that matter of fact, like in the case of cavitation, then you would have to specify some extra options. In this case, all I'm concerned about is the surface tension between water and air, because that will definitely dictate the shape of the boundary between those two phases. So what I do is I go ahead and select the constant option from the surface tension coefficient, and then I enter a value. And on the bottom left over here, you will notice that I have checked the surface tension force modeling option and chosen the continuum surface force. This is because I want the forces to be considered. I think this is the more conservative form of solving the equation, so it's a little bit more accurate. If you had more under-resolved regions in your computational domain, then you might get away with choosing something like continuum surface stress, because it's the more conservative form of solving the equation. So for this case, I'm just going to go ahead and stick with continuum surface force. And then you will notice this other tab here, which I was talking about earlier. For example, if you had that evaporation, condensation, mass transfer mechanism, wherein one phase is changing into another, you could simply add more mechanisms over here, and it would ask you to, specify the mechanism of mass transfer between your primary phase and your secondary phase. Right now, there is no mass transfer between water and air, so I'm going to go ahead and keep this at 0. And with that, I'm just going to go ahead and hit apply. And then close this panel over here. In the materials stage, you will notice that I have both air and water specified. Both air and water are incompressible in this particular problem. If you have a compressible gas in your particular application, make sure you choose the properties accordingly. And then we are going to go ahead and look at the cell zone conditions. And the only reason why I'm doing that is because I want to open the operating conditions panel and double check that gravity is check marked, because we have an important effect of gravity in this particular simulation. And if you're choosing VOF, I think the best possible option over here for operating density is the minimum phase averaged. I think that is what Fluent recommends. But you could also go ahead and choose, air density of 1.2 if you wanted to for this particular problem. And then let us look at the boundary conditions. So we have water coming in over here for a specific amount of time, right? So I go ahead and select the inlet boundary condition. And when I have a multi-phase problem, what Fluent will allow you to do is specify certain settings for each of the phases and the mixture as a whole. So right now you will notice that because multi-phase is turned on, you have this drop-down menu at the top that lets you toggle between the 3 different settings. One is for the mixture as a whole, and then you have individual settings for water and air. So for the entire mixture, this looks to be good to me. The direction specification is normal to boundary. And then for water, we're going to go ahead and specify a mass flow rate of 20 kilograms per second. And then if I go ahead and change it to air, I'm just going to keep it at 0 because at no point is air entering in the inlet, through the inlet. So I'm going to go ahead and close this one over here. And then the outlet is over here. So both these, it is clearly indicated in the GUI over here. Wherever you can see the red arrows, all that is outlet. And even at the top over here, it's 0 gauge pressure. So if I go ahead and look at the outlet, you'll notice that, the gauge pressure is specified as 0. And again, you will see that, there are 3 different options for this particular case. You have mixture, water, and air. Now, one thing you have to keep in mind when you're setting up these VOF simulations is that at the outlet, you want the right phase to enter in the backflow condition. So if I go ahead and choose air, you will notice that I've specified a backflow volume fraction of 1. When I specify a backflow volume fraction of 1, what I'm basically dictating is that if there is any reverse flow, then only air enters the system and not more water. Because if water enters the system again because of reverse flow, then it can mess up my simulation. So I'm just going to go ahead and specify a volume fraction of 1. Now keep in mind from my presentation earlier that the summation of volume fractions of all phases in a mixture is 1. So when I specify that the volume fraction of air is 1, I'm essentially telling Fluent that the volume fraction of the remaining phase, water, is 0. So it's complementary that way. Now, I'm going to copy the same outlet boundary conditions to this other boundary at the top. So you will notice that this has the same boundary condition. So once we have the boundary conditions all set, we are going to talk about marking a region in my domain so that I can fill it with water at the very beginning. So I told you that, a certain portion of this tank at the beginning is filled with water. Now, in order to make sure that the correct boundary is filled with water, or the correct portion of the domain is filled with water, I need to mark off some cells in my domain wherein I can patch in that volume fraction that I desire. So what I can do is I can go ahead and click on cell registers. And like I said, this has already been set up in the before, this AVA session. But what I've basically done is I've marked the height of the tank that I want to be filled with water at the very beginning. So you can specify the extent of the domain in terms of the XY coordinate and choose that particular region, which you will later on patch with the desired volume fraction. So if I go ahead and click display, you can see that this is the level of water that I initially want in the tank. It's not filled with water yet, but the cells are marked. So hopefully that is clear. And when I'm done marking this cell register, I'm going to go ahead and look at calculation activities. In the case of calculation activities, because I want to get an animation out of this particular demonstration, I'm going to autosave it after every 50 time steps. Okay. And what I've also done is introduce some execute commands. Now, what are these commands? These commands basically tell Fluent when to stop the influx of water through the inlet. So remember I said that after a particular amount of time, I'm not going to let any more water come in because I want to see how the tank is emptying. And if the water keeps coming in, then that difference will not be quite visible. So what I go ahead and do is I put in a text command, which is supposed to be executed after every 100 time step. And based on the time step size, you will notice that I think the water is allowed to run for 0.25 seconds, if I remember correctly. So after 0.25 seconds, what I'm basically telling Fluent to do is to change my inlet from a mass flow inlet to a pressure inlet. If it changes from a mass flow inlet to a pressure inlet, then there's no more chance of water or air coming in. So that's what I have defined over here as an execute command. So after I do that, one very important step is to make sure that we choose our time step correctly and also choose the methods correctly. Now, for multi-phase flows, the convergence and the trend of convergence during simulation can be very sensitive to your initial conditions and your iteration parameters. So make sure that you review the Fluent recommendations in theory guides and user guides before you go ahead and set it up. If you need additional guidance, again, feel free to reach out and I'll be happy to help. In this case, I've selected the PISO scheme, and this is the standard recommendation for VOF models, and then, kept the defaults as it is. So now that I've done that, I also want to see, what time step size I want to assign so that I know exactly when my water is being stopped. So like I said earlier, it says that after every 100 time step, or in fact, after the first 100 time steps, change the inlet condition from a mass flow to a pressure inlet. So after 100, time steps, we would have 0.25 seconds, as you can see from the time step size. So that's when we're cutting off the water, right? So we, set it up accordingly. And then because we want to patch this initial region with just water and no air, I'm going to show you how to go about and do that. So if you go to initialization, I'm going to go ahead and initialize this domain. Once I initialize this domain and look at my domain right here, so I've changed the color map scheme. Instead of red, blue, and green, it's using this grayscale. This is just to highlight the difference between 0 and 1 volume fraction. You will notice that the volume fraction of water everywhere is 0. That means this entire tank is empty and it is filled with air. Remember, 0 for water means 1 for air, right? And this happened because when I was initializing, I put 1 as the air volume fraction. Now I want to specify that the volume fraction in this particular level, this region, is 1 for water. So what I'm going to go ahead and do is click on patch, and then I'm going to choose air. Notice that water was not visible in the drop-down menu because only the secondary phase can be assigned an initial patch value, which is why I said that, be careful about how you specify the primary and the secondary phases. So once you select air, you can select volume fraction. And then it already has this register, this region that we marked out earlier, selected over here. So I'm going to go ahead and stick with the value of 0 and then hit patch. When I do that and look at the contours again, now you notice that because I patched that initial value of 1, this particular region is filled with water. So I'm going to go ahead and close this and run my calculation. What you will notice is that as the time steps progress, the level of water keeps increasing, which means that the water is coming in through the inlet. And I want to see how this interface changes over a period of time. And as the time steps keep progressing, we'll be able to accurately capture this boundary. And once it hits the 0.25 seconds mark, you will notice that there's no more water coming in from the inlet. If anyone is curious, I'm using 4 cores on my computer. This is just a simple 2D problem, so doesn't require that much hardware. So you must have noticed that there's no more water coming in because we're past that 0.25 second stage. And as the water keeps filling and siphoning down, you can easily track the interface. And because I'm auto-saving, after every 50 iterations, these snapshots for the contour will be available to, create an animation later. So this was just a, very simple, but in my opinion, effective way to display how, just a few settings in Ansys Fluent can give you so much visibility to this very dynamic behavior of how the interface between these two phases changes. And, you could use the same principle, same sort of setup for so many different applications. John, are there any questions for me? John?
Yes, Snehda, yeah, can you hear me?
Yes, I can hear you.
We have some questions. One's for earlier, and it has to do when you were talking about the surface flow and the bubbly. So so the first question was, how do we handle where the problem has free surface flow and bubbly flow? Example, flow in a pump installed in an open, and I don't think they completed the last word, but it sounds like flow inside of a pump.
So there are, different cases in which you see more than one phenomena, or, when you have these different types of secondary phases, dispersed in your primary phase. There are different ways of going about it. Some of the models, take into account everything. For example, the Eulerian phase that I was talking about earlier, because it solves individual equations for all the different phases, it can be really accurate, but also time consuming at the same time, wherein it'll be able to capture all these individual phenomena correctly. But sometimes, approximations also work. Like, for example, even though VOF is more suited for a type of simulation wherein you're trying to capture the boundary, but if you don't think that boundary is that important, you could go ahead and just use VOF as a blanket model for something of that sort, wherein you just need to make sure that the computational grid is small enough or comparable enough to the boundary of those bubbles that you're talking about. So it'll definitely take care of the free surface flow. But for those small bubbles, if your computational grid is sized as such that it can capture the interface, then you can do both the things with the same model, if that makes sense. But of course, with individual applications, it can get a little complicated depending on what you're trying to do, and that would require a little bit more investigation. But sometimes your mixture model, your VOF model, is multi-purpose, and you can use it to capture different types of phenomena in the same mixture.
Okay, and then the second question we have is, when is it better to use implicit body? I'm not sure what that is.
Yeah.
as a structures guy.
So from what I know, implicit body forces can be used in turbo machinery, and in cases where surface tension is very important for capturing the shape of the boundary between the different phases. It lets you it lets you capture the details with more accuracy. So if you want that extra level of accuracy in your simulation, wherein that the forces in the domain are playing a big role, for example, in boundary separation, or flow separation or something of that sort, then I would suggest go ahead and use the implicit body force option in the VOF setup. Any other questions, John?
That's it for now.
Okay.
Please want to Snigdha to elaborate on anything that you see here. Okay, questions are coming in now.
Okay.
Can we have this model to go over? Okay, so if you could share the study that you did.
Can I share the study that I did, like the files, etc.?
Yeah.
Yeah.
Yes, Saeed, we could get with you afterwards and have a
Yeah,
discussion.
this is a generic case, so I don't think it should be a problem. Yeah, for sure. And any other questions, John? Like, because this is it, like this is where I end the demonstration. I'm just, looking at the graphics and, looking at CFD animations always pleases me. So looking at the screen.
Yeah, it's mesmerizing to just see the flow going through.
So yeah,
I think that's it. Yeah, that's the we had those 4 questions.
So with that, yeah, feel free to leave us, feedback in the survey that you guys can see after this ends. And thank you so much for joining us today. We'll see you again next Tuesday.